Here we're going to present a proof of the Pythagorean theorem. Before that, let's take care of some background material. First, the statement, the whole is the sum of the parts, which is simply the following. If point X is between A and B on segment AB, then AX plus XB equals AB. The length of segment AX plus the length of segment XB is the same as the length of the whole segment AB. Here is some remark about that statement. It is taken as a postulate in introductory treatments of geometry. In more advanced treatments of geometry, it is proved from more elementary statements. There are a couple of references there. Elementary Geometry by Gustafsson and Frisk is an introductory treatment of geometry, so it is a postulate there. Greenberg's Euclidean non-Euclidean geometries is a more advanced treatment, and there it is proven as a proposition. Now, our next statement, very well, many of us are very familiar with it. In Euclidean geometry, the interior angle sum of any triangle is 180 degrees. We can find proofs of this in various places. Here I have a couple of references. One of them is Gustafsson and Frisk, Theorem 3.8. Another one is Musser-Trim's College Geometry, Theorem 5.9. Alright, now let's take a look at a preliminary lemma that's going to help us prove the Pythagorean theorem. Will help us with our proof of the Pythagorean theorem. It says the following. If you are given a right triangle ABC with an altitude drop from C onto AB, call it CD, in Euclidean geometry, then one of the conclusions is that this leg squared is the product AB times AD. So AC squared is AB AD. Similarly, BC squared is AB times BD. Those are the two conclusions we get. Now what I want to do is write a proof sketch. I'm going to sketch a proof of this. It uses similarity. It uses a fact about similarity which can be proven. We're not necessarily addressing that fact right now, but it's the following. When two triangles are similar, then corresponding sides are in proportion. So we're using that fact here. So here is the given diagram of our lemma. And here is the same given diagram, but without the altitude CD. We are going to note that in the small triangle is in some way similar to the larger triangle, the largest triangle. It happens to be as follows. Angle A is congruent to angle A. The right angle is congruent to the right angle. So because the interior angle sum of triangles is 180 degrees in Euclidean geometry, then this third angle, the smaller angle, is congruent to the smaller angle, the big triangle. So that makes our two triangles congruent, our two triangles similar. So triangle ADC, triangle ADC is similar to triangle ACB. Consequently, AC is to AB as AD is to AC because of similarity. When you cross multiply, you get AC squared equals, you get AC squared equals AB times AD. AB times AD. That is one of our conclusions. Okay, in a similar fashion, if we look at the right triangle now, in the largest triangle, we get similarity as well. Let me erase these references now. Let's take a look at which angles are congruent. Well, B with B, the right angle with the right angle, therefore the third angles have to be congruent, again because we're in Euclidean geometry. So we get triangles DBC, and triangles CBA are similar. So what do you get from that? You get that BC is to AB, BC is to AB, as BD is to BC, the larger leg to the larger leg. So cross multiplying in that proportion, you're going to get BC squared equals AB times BD. And that completes our preliminary lemma. Now let's take a look at the Pythagorean theorem. We're now ready to address the Pythagorean theorem. Here it is, there it is. You have a right triangle ABC, side A opposite to angle A, side B opposite to angle B, and side C opposite to angle C. That makes C the hypotenuse because angle C is the right angle. That triangle happens to be in Euclidean geometry. So what's our conclusion? Our conclusion is that A squared plus B squared equals C squared. The sum of the square of the legs is the hypotenuse squared. We are very familiar with that statement. In our earlier studies of mathematics, we have seen the Pythagorean theorem. Now, I'm going to address the proof. I'm going to address a proof of it. It makes use of our preliminary lemma. I'm pointing the camera to cover the whole proof. First, a construction. On our given diagram, we're dropping altitude from C onto AB. We're labeling it CD. So here's our proof. First, the diagram as labeled, that's given. Second, CD is perpendicular to AB. That's because of our construction. All right, here we're going to note that the preliminary lemma applies. AC squared equals AB times AD. AC squared, AB times AD. BC squared, AV times BD. That's the preliminary lemma. Now let's add BC squared plus AC squared. BC squared, this is a little backward, so that's because I wrote this a little carelessly, but here it is. BC squared is AB plus, BC squared is AB times BD. AC squared is AB times AD. Factor out AB. What do you get? AB times AD plus BD. AD plus BD is the same as AB because of this whole is the sum of the parts. So let's make a substitution. AD plus BD becomes AB. So we substitute it. Therefore, BC squared plus AC squared is AB squared because AB times AB is AB squared. This pretty much is what we're after because BC is A, so BC squared is A squared. AC is B, so AC squared is B squared. And AB squared, well, AB is C, so AB squared becomes C squared. That completes our proof.